All right, thank you very much for the introduction. Before I start the talk, I want to quickly ask who of you is familiar with WebAssembly? All right, perfect. Still some people who are not raising their hands. That's perfect because I prepared a very short introduction. Does this work? Perfect. So everybody knows JavaScript. The way to make the web interactive, we use it to execute foreign code in our web browsers on our device. Pretty interesting. That's why it's executed sandboxed. To get some better performance with it, normal JavaScript runtimes should compile JavaScript, but still, like executing a full video game in the browser will still be a problem performance-wise. So the idea was to reuse traditional high-performance languages like C, C++, and Rust, which are like easily optimizable, or we know how to optimize them. We have working compilers for them, which have been built for many years now, and use them for compilation for the web. So there was a subset of JavaScript, this is still valid JavaScript called asm.js, which didn't use all the features, and then browsers could be optimized for execution of this subset of JavaScript. There was still too much overhead with executing asm.js, for example, for validating that it is actually valid JavaScript. So the movement now is to have a separate runtime in browsers and a separate bytecode, which is not JavaScript, which can be further optimized, and also the runtimes can be specifically built for it. This bytecode is WebAssembly. So the big benefit of WebAssembly compared to JavaScript is that we can reuse existing architectures to optimize this code, and also this code is statically typed, so we have way more optimization potential. All right. Alexis and I have been looking at bounce checks in WebAssembly, so I want to quickly introduce where we would encounter such a bounce check. In general, WebAssembly is executed, as I said, in a sandbox execution mode, so we can't access any memory that we didn't allocate. This is where this bounce check comes into play. Here's an example. I show you a very basic WebAssembly function, which just accesses some random point in memory and then drops the result. So looking at the first line is a local.get. This would be used to get the first parameter of our WebAssembly function. Let's assume the value was 0x40, which we then put on the WebAssembly stack. As you can see, WebAssembly is stack-based. So now we have that on the stack, and we want to continue with the load. This load instruction is a 32-bit integer load, and we can also specify an offset and an alignment. The alignment can be ignored for now. The offset is very important because it is a separate 32-bit integer encoded into the load instruction, which is added to the immediate pulled from the stack. So in this case, we take the 0x40 and add the 2 as the offset to get our whole address that we want to access in the WebAssembly memory. The WebAssembly memory can be seen down here in the slides, a schematic of it at least. This is in 32-bit mode, which means WebAssembly memory and the normal WebAssembly is accessed with 32-bit addresses. As can be seen here, our maximum memory size is 4 GB. The runtime doesn't have to use all this memory though. So in this example, we only allocated 256 KB, which is available to the WebAssembly code. This can be increased dynamically through instructions, or also can be specified as a minimum at the program start. All right. When we develop our runtime now, our job is to figure out where will this load hit our memory. Like, will it be 1 or 2, which are completely valid memory accesses and we can just load from memory, or will it be 3, which hits unallocated memory, which is not accessible by WebAssembly. So this should raise a WebAssembly trap. It is actually guaranteed to raise a WebAssembly trap, which basically means we abort the execution of the current WebAssembly thread. So this has to be determined by the runtime. And we'll look for how we can do this and how we can optimize this. And the rest is just easy. We assume this was 1 or 2, a valid memory access. So we get whatever we loaded from memory onto the stack, and we can drop it again. That's basically how WebAssembly works, how we could execute it. But we want to look more on these bounce checks and how we figure out whether this memory access was actually valid. So what one could come up with, a pretty easy solution is just, well, we know the size of the memory, we know the address where we want to load from, why not just compare them? And if my address is larger than my memory size, I can just jump to some code that performs a WebAssembly trap. Easy solution has 2 big problems. We introduce a branch, which is here the conditional jump. We hope that our branch predictor predicts this jump is not taken, but these are branch predictors. We have to trust that. And also one problem that is not too clear from here is in line 2, we're loading the memory size. Let's imagine this is a multi-threaded execution of WebAssembly, which is possible through the threaded threads proposal. Then this memory size could just have been changed by some other thread. So this is actually a cache miss, which could increase execution times a lot if we constantly resize the memory. So this load is also a problem. Even though this is such a problem, it is used by some runtimes for every memory access. Anyways, even the original WebAssembly paper already introduced an optimization of this. Normally, we will execute WebAssembly on 64-bit host systems, which means we have a 64-bit memory, or 48-bit, for example, virtual addresses for Intel CPUs. So we can actually just allocate our whole 32-bit address space of WebAssembly, which is 4 GB. Not really, because as I mentioned before, we also add a 32-bit offset to the 32-bit address that we pull from the stack. So the entire address is actually 33-bit long. So if we were to allocate the whole addressable memory, we actually have to allocate 8 GB of memory. On our 64-bit host system, no problem, we can do this. And then we just say, okay, every page that is not accessible via WebAssembly, we just protect this. So on a Linux, for example, we do an mprotect with prot none. So every access to that memory will just fail and raise an exception. Pretty straightforward, as you can see. Our assembly, this is Intel assembly, by the way, sorry, for x86 CPUs. You can see our assembly reduces to just the memory access, which is nice. Memory pointer stays the same, so this can just be kept in some register, even we don't have to load this from memory every time, which is very fast. No overhead for bounce checking because everything is done by the MMU. This is very popular and pretty easy to implement, so this is also used by most runtimes for 32-bit addresses. There's one last problem though, how do we get from the invalid memory access, which raises an exception in the CPU, to the WebAssembly trap? We have to do this, this is more an engineering effort. The paper I'm presenting was written for a database system that my chair develops, which is called UMRA. This is just a basic context to know we're writing our WebAssembly runtime in C++. And in the end, we generate LLVM code that is then compiled there. And this is not too important for the bounce checking, but just to get the bigger context, why actually going from a CPU exception to a trap can be kind of cumbersome. Because we have to go through the Linux kernel, which will generate either a segfault or a SIG bus signal, depending on where we hit the memory. which will actually then call a signal handler for us, which we have to register. From the signal handler, we can't just long jump to some trap handler because we might have some resources open, so we need to call some C++ destructors. That's why we need to raise a C++ exception from the signal handler. This is not as easy as it sounds, because normally a signal handler is not a normal stack frame. You can't just unwind through this. But LLVM and GCC generate code to do this. So we can actually do this safely and then unwind through our stack to find somewhere the end of our runtime and finally count this as a WebAssembly trap. So there are some engineering efforts also behind this, but basically we trust the MMU to raise some CPU exception and then raise a WebAssembly trap from that. All right. So much for the background. Now the big problem. We're moving to 64-bit WebAssembly addresses. This is still a proposal, but it's important because some WebAssembly code might need more than 4 GB of addressable memory. And imagine game engines, for example, running in the browser might just need more memory. So just allocating all the accessible memory is kind of a problem because that's more than our host system can actually provide. So our 32-bit guard page approach, which I just showed you, doesn't work any longer. So we need new bounds checking methods, and that's what we explored. So we present two bounds checking methods today: the 64-bit guard pages and the 2-level guard pages, which are basically two improvements of the 32-bit guard pages for 64-bit WebAssembly. One problem that I already mentioned, 32-bit WebAssembly actually ends up with 33-bit addresses. The same is true for 64-bit WebAssembly, which ends up with 65-bit addresses, which are a way bigger problem than 33-bit addresses because they don't fit in our CPU registers, they can't be used as address operands, and every arithmetic operation where we try to combine the immediate and the address just results in an overflow. So until the end of this presentation, we will just assume that addresses are wrapping in WebAssembly. The current proposal does not do this, but I will present options how to mitigate this issue. All right. So the first approach that we discovered with 64-bit guard pages, the basic idea is you will never need your whole 64-bit WebAssembly address space. So we just statically reduce it down to a smaller address space, which we do by applying a mask to your address and just checking whether the upper X bits are set or unset. Here, for example, you can see it. We just artificially shrink down the 64-bit address space down to 4 GB of addressable memory again, so like with 32-bit addresses. By comparing your upper 32 bits with a mask, and if one of these bits are set, we can then again do a jump to some trap code that executes a trap, and if not, we can just go on. No, you might say, well, this looks exactly like the software bounds check I proposed at the beginning. We just don't do a compare, we now do a test with a mask. Well, for this, we don't need the memory size because oh, sorry, this is one thing I forgot to mention. Of course, the subsequent memory access we can then do with our normal 32-bit guard pages. So we just look whether we would overshoot our guard pages, then we jump to the trap code, and if not, we can just reuse what I showed for 32-bit WebAssembly. So this eliminates the need for loading the memory size, which should be good in multi-threaded environments, but we'll see in the benchmark how this turns out. The most promising approach we are presenting are 2-level guard pages. These also build on the idea of the 32-bit guard pages I presented for 32-bit WebAssembly, but enable us to actually cover our whole 64-bit address space with guard pages. All right. So here you can see the schematic. The WebAssembly memory and the microguard pages together can be seen as our as one unit, as we've seen then before for 32-bit guard pages. But now we can't just increase our microguard region to the size of our memory, because then again, our memory, our virtual memory on the host machine is just too small for that. So we basically compress chunks of memory down and map them to one macroguard page in the macroguard region. Here you can see, for example, we always take a 2 gigabyte chunk of memory and map it to one microguard page in the microguard region. So addresses 0 to the address that hits 2 gigabyte minus 1 maps to microguard page 0, and all subsequent addresses to microguard page 1, and so on. Oh, sorry, no, not 2 gigabyte, 1 gigabyte. You got this confused. So for the actual access in the assembly, we first get the address, then scale it down, do some more arithmetic with it. This is basically just to calculate the address of our macroguard page. Do an access to the macroguard page in line 6. We never look at the result, because we don't care about the result. We just care about, is the macroguard page protected or is it accessible? If it's accessible, perfect. We can continue with our further memory access, which is the actual load in line 8, which then just accesses the address. And in line 8, this performs again a bounce check against the microguard region, which serves the same purpose as we've seen for 32 bits. It just protects the rest of our block, in this case the 1 gigabyte block, which is not yet allocated by WebAssembly. So again, in this example, you have 1 gigabyte plus 1 page of WebAssembly allocated, and the rest is not available to WebAssembly. So every access to 1 gigabyte plus 1 page and further either hits the microguard pages, which is a seg fault, or hits behind this 2 gigabyte line, which would hit macroguard page 3, or 2, sorry, number 2, and also is a seg fault. So we can actually make sure that for any further 64-bit address, you will only not get a seg fault if you hit valid WebAssembly memory. All right. Some further numbers for this. We can also calculate the perfect ratio between macroguard region and microguard region size. Basically, you could already imagine the smaller my microguard region, the smaller my chunks. So in this case, it wouldn't be like 1 gigabyte, but it would be 512 kilobyte or something like that. Then I need way more macroguard pages. Each macroguard page requires 4 kilobyte of memory for x86. So that also requires more memory. We can see that the optimal size of both is if they're both the same size. And then we can just find the minimum size for both, which turns out to be 256 gigabytes for each, so 512 gigabyte for both the microguard region and the macroguard region together for Intel x86 CPUs, and a WebAssembly page size of 64 kilobytes. All right, now the most important thing, does it actually work? Is it faster than software bounce checks? And therefore we performed some benchmarks. These are 4 benchmarks from the spec CPU benchmark suite. Why only 4? There are so many more. Well, these are the only 4 we were able to compile with the current WebAssembly toolchain without modifying the benchmark. Some other benchmarks are very low-hanging fruits, but you would have to modify either the compiler or the benchmark. We didn't want to do that. And also a self-written k-means benchmark, which was written specifically for our database runtime. All right, this is disclaimer, this is only single-threaded. So what we can see here in, I'd say, dark green is software bounce checks. perform almost similarly to our 64-bit guard pages. As said, this is single-threaded execution. We expect that 64-bit guard pages might have an advantage for multi-threaded execution, but for single-threaded, they're as bad as software bounce checks. As you can see, this is normalized to execution without any bounce checks, because a valid WebAssembly program only accesses valid memory. So you can also execute it without bounce checks, but of course then it's not sandboxed any longer. In dark blue, you can see the 32-bit guard page approach. As we expect from the assembly we've seen before, there are no instructions introduced for the bounce checks. We just use the MMU, no overhead at all. And in light blue, you can see our 2-level guard page approach, which performs very well, like, I don't know, you can see it somewhere around 11% or even a bit more overhead. Is really good compared to sometimes like 2.4 times execution without bounce checks when you use software bounce checks. Yeah, that's basically it. I've got some more slides which handle the 65-bit thing for truncation. Yeah, I go through this quickly. They are more thought of as a discussion topic, probably, because currently we wrap 65-bit addresses. Again, we have 65-bit addresses because we take a 64-bit integer from the stack and add the 64-bit immediate that is encoded into the instruction. We currently just wrap them or accept the integer overflow. This might yield to false positives, so you might not get a trap even though you were supposed to get a trap. This is not a security issue though. Like, you will just access wrong memory. But it's still your runtimes memory, not some out-of-bounds memory. This is not spec compliant. So this is a problem because you're guaranteed to have a trap. So option 2 is we actually are spec compliant and handle these 64-bit addresses. There we have multiple options. Like the offset that is added is statically added. So if it's 0, we can just go on. There will be no overflow. Perfect. And then there are some possibilities how to check whether we will have an overflow. Every integer overflow is invalid, so as soon as we know that the offset and the address together are larger than 64, larger than anything that can fit into a 64-bit integer, we can just trap. So maybe our CPU offers some option to detect overflow when we combine these, and we can then trap. That would be perfect. Or we also wrote down some idea here. There are many other ways how to check this. I'm not going to go into details here. Yeah, I think that's enough for that. There are possibilities to check whether you would have an overflow for combining these. All right, and that's already everything I had to talk about. I presented you the 2 approaches for 64-bit bounce checks for WebAssembly and our benchmarks. Thank you very much for listening. Yes, any questions?
Yeah, I kind of wanted to ask because when you're talking about when we allocate, for example, 4 gigabytes of the VM memory, how is that really, how are we allocating 8 gigabytes? I don't think we are. If you ask the operating system to allocate you null pages that are going to trap on the page fault, they don't get allocated actually. I think they just are non-existent. Like when you access that memory, virtual memory, it generates a page fault and then the operating system just says, yeah, that's not a legal memory to access. I think there may be a problem when you have 64-bit memory because there's a lot of pages, but I don't think you ever allocated much memory. I don't think where you have WebAssembly memory of 4 gigabytes, you allocate actually 8.
So if I get your question correctly, so the first thing with allocated and unallocated, every thing where we say like we allocate these full 8 gigabytes, but we only make, I don't know, less than 4 gigabyte available to WebAssembly. What we actually do is, of course, the actual memory is allocated and somewhere in your RAM. The rest is just a shared copy of /dev/0, I think. There's no page that is actually allocated. It's just an entry in your page table that will be used for these inaccessible pages until like you have the 8 gigabyte full.
Do you need an entry in the page table though? Yeah, maybe. Sorry.
If you don't have it, your operating system could just place some other thing in there. Like if I then do a subsequent mmap call without providing an address, I could end up with another allocation in the space, which would then result in a false positive too.
Thank you. It's interesting. For the 65-bit, couldn't you do the 2-level thing, but just shift your both your offset and your base number before you do the comparison? So basically, do the same trick as you did with the 2-level one, except don't add the numbers. Shift them both and add the shifted number, and then you could do the 2-level one just the way you did before.
I didn't think about this before. It sounds reasonable. I might have to think about it a bit more, but yeah, that could work. Yeah, because we only have to make sure that it doesn't overflow. So, and then of course we can also do the bounce check with the pre-shift. Yeah, that's a very good idea. I didn't think about this. Thank you very much for the suggestion.
Hi, I'm surprised at the results. So yes. So I was wondering why the 2-level guard page is much faster than the 64-bit guard pages. The 64 guard pages the 2-level guard pages accesses memory twice compared to the while 64-bit guard page access memory once, but it performs the branch instruction.
Yes. So for the 64-bit guard pages, you have the additional branch instruction. And if I jump back, you have to store this mask somewhere. So either this is a second memory access, or you have a register that you block for this. So we checked multiple ways to do this, a test with memory or using a register and stuff. This was actually the fastest one, so we stick with loading from memory, because that's then in your cache and it's pretty fast. But was your question why this is so much slower than the other one?
Yes.
So here it is important to notice that both memory accesses are completely independent. So your out-of-order execution can actually shift them however it wants to, and can also do the arithmetic calculation of your macro guard page address out of order. So we think at least this is a big opportunity for the CPU to optimize the execution of 2-level guard pages in particular, because you don't have that barrier of a branch between.
Thank you. I understand.
Thank you very much.
One more question. Time for one more question.
I think it's also true that you can lift the first level check out of a loop, because you can, even if the loop wraps around, you're going to go out of bounds.
So if you were to access memory in a loop, or
yeah,
so this is also something we didn't cover at all in this paper. This just assumes that every bounce check is required. Of course, if you, for example, have a loop that goes through an array or something like that, you could also statically eliminate some of the bounce checks.
Even just the first level, you can just lift the first level.
Yeah, so if the loop stays in the same region that is covered by the same microguard page, yes, you can lift this outside of the loops. Yeah, that's also what we didn't look at. We just, in this research, we assume that every bounce check is completely new and required, yes.